Welcome to the final section of chapter 16, where we look at centripetal forces. So immediately before Isaac Newton got involved with circular motion, Christian Huygens in Europe had looked at this idea that an object might be compelled outwards when swung around in a circle, calling it centrifugal force. And indeed, the water in a bucket swung over your head does definitely seem to be compelled outwards. You are pressed towards the sides of a spinning ride. So what is this thing? Well, Isaac Newton looked at it and he thought maybe we're interpreting this all wrong. He thought, what makes something whirl around like a bung on the end of a string spun around? Well, it's the tension in the string pulling it back towards the center. And if you think about it, if we remove that tension, if we cut the string, then what would happen to the object is it would be flung away tangentially in that straight line. That rectilinear motion flinging away is what Huygens had mistook for an outward-seeking force. Really, it's a consequence of Newton's first law. Without that force changing its motion, the object would continue in a straight line. So Newton described this center-seeking force as centripetal, which basically means in Latin, a force aimed towards the center of a circle. Of course, it was Newton's second law that said that force was equal to the rate of change of momentum, mv minus mu divided by t. The physics of car crashes and why they hurt when you're going really fast and brought to a halt in a short interval of time. So the change in momentum, delta mv, divided by the time interval, that is what gives the force that created that momentum change. So if we move the m out of that, and we realize that it's the change in the velocity divided by the change in time, well, we've seen that before. The rate of change of velocity is equal to the acceleration. So when the mass is constant, the special case, F equals ma. Force is equal to mass times acceleration. So of course, we can substitute our two centripetal accelerations into this formula. Remember from the last lesson, we had the acceleration in terms of the linear quantities, which was v squared over r. Now, if we substitute that into F equals ma, we get that the force, the centripetal force, is equal to m v squared over r. This is known as centripetal force in terms of linear velocity. But of course, we can also substitute that other version of centripetal acceleration, omega squared r, to give us F equals m omega squared r, which is the centripetal force in terms of angular speed. So what would happen if centripetal force ended? Well, in the case where the orbital motion of planets is provided by the gravity acting as the centripetal force, if the gravity disappeared, then what would happen is the objects would continue flying along in a straight line, tangential to the circle they were moving around in a straight line with the same velocity vector as they had at that moment when the force disappeared. Now we all know this because we've all spun something around on a string and let it go and seen it fly away. And so this centripetal force is the thing that is pulling things around in a circle, affecting the change in momentum that comes with the velocity vector changing direction. Now this is where it gets complicated. Everything we've done in circular motion has been very straightforward, but there are some applications of circular motion at A level that can be quite tricky. Bearing in mind, in year 12, a lot of the things that we were doing were breaking forces into their horizontal and vertical components. It might be worth going and having a recap of what we had to do in those instances. Another thing that's important is understanding that the normal force is always at right angles to the surface. If a car was going around a banked track, then what we'd find is that the centripetal force would be being provided by perhaps a combination of the friction, but also the horizontal component of the normal force. So if you look at this diagram here, well, the horizontal component Fn is sticking out at right angles to the track. The vertical component Fn cos theta has to be equal to the weight mg, otherwise it would fly off into space. And so that unresolved force, that unbalanced force to the right, the Fn sine theta, well, what does that do? It's pulling towards the middle. That is going to make this car go around in circles. It is equal to the centripetal force. So if Fn sine theta is equal to mv squared over r, then what you could do is, using every other bit of information, including the curved bank of the track, the normal force, which you could find from the weight of the car and the angle of the slope. You know the mass of the car. Could find, for example, the velocity that it needs to go around in this circle to provide this force, or in fact the radius of the circle. So Fn sine theta equals mv squared over r is really powerful. And if it's not self-evident, I would actually remember that. It's not given explicitly in the formula booklet. So it's one way you've got to remember that it is that horizontal component of the normal force, which you can calculate, that is going to provide the centripetal force of a banked track. Of course, if the track is not banked, it's a flat track, it is only friction that is going to enable the car to go round a circle. If it goes round at greater angular speed or shorter radius, then what you're going to find is that the friction is going to have to be higher, otherwise that car is going to fly off in a straight line. Another question involving circular motion is the vertical circle, something doing a circle vertically with gravity assisting along the way, like a conker swung over the top, or a fairground ride that sends you over the top, or even something like a Ferris wheel. What is the physics that we need to apply to understand the forces involved in making this work? So let's think about the conker going over the top. It could be a ride, but we'll talk about it in terms of a conker. Now think about what is the perception of weight. Now normally when you stand on the ground, your weight is actually acting into the ground and you are oblivious to that. But your perception of your weight is the reaction force of the ground pushing back at you in the opposite direction to weight. Your perception of your weight is actually the negative of your weight, acting upwards. That is what we perceive as our own weight. Now think about this object. As it's going over the top, then the apparent weight at that moment, how much weight you feel, is going to be equal to the centripetal force pulling you downwards, taking away the opposite of your weight. Now, the reaction force to your weight, which is normally acting downwards, will be acting upwards. So we put a negative sign on it, because if we've defined weight as downwards, then weight acting the other way would be negative. It would be. And so what we find is that the downward pull of centripetal force is being cancelled out by the reaction force to your weight. And so at the very top of the circle, you experienced a condition of weightlessness. Now, as you travel around, and you can actually find that the condition for weightlessness, because mass cancels out and mv squared over r equals mg, we find the condition for weightlessness is that the velocity going around the circle is equal to the square root of the radius of the circle times the strength of gravity. Now, you could just derive that expression in the moment. You don't need to remember that, but I do recommend keeping in your memory that at the top of a vertical circle, your apparent weight is mv squared over r minus mg, and that the weight at the top is at the least. You could find exactly the right speed for the radius to have mv squared over r equal mg, and at that point you would be weightless at the top. And at the bottom, because your centripetal force is acting upwards and your the reaction force to your weight is acting upwards, then it's the actual weight that you would feel would be mv squared over r plus mg. And so on a roller coaster, as you go upside down, you feel weightless at the top, but you pay for it when you come underneath, because you might feel twice as heavy at the bottom. This is where we get the expression like 2Gs or 3Gs. Like 2Gs is just twice as heavy as you otherwise would be, and you feel that when you go on the underside, like the bottom of a loop on a roller coaster. And we can use this to great effect, because it means that we don't have to go upside down to feel weightless. In fact, it's just a parabola that is needed. As soon as you go into free fall over the top of a parabola like this, then what happens is you're going basically on the top part of the circle. And so long as you follow that trajectory, then what's going to happen is you're going to have the mv squared over r minus your weight, and so you're going to feel weightless as you go over the top. You pay for it at the bottom where you experience several G's as the plane pulls out, but it means that on this NASA aircraft, the Vomit Comet, that you can actually experience weightlessness for like 30 seconds at a time to train for missions in space, where because the space station is always falling, it is always experiencing the condition of weightlessness. Another favourite question involves the conical pendulum. So rather than just swinging backwards and forwards, someone's given this sideways motion. Round it goes around the centre point. Things to define include there's the weight acting down, mg. There is the force of tension acting in the string, F. The vertical component of that force is F cos theta, and the horizontal component of that force is F sine theta. There's R, the radius of the circle at which it's turning around. There's H, which is how from that center point up to the ceiling. There's L, which is the length of the chord. And through like a Z angle approximation, there's two thetas in this. The theta between the tension F and F cos theta, the vertical component, is also equal to the angle at the top of this cone, measured from the midpoint, that is. So there we have it. We have two components. We know the vertical component F cos theta has got to equal mg acting down, and that the horizontal component F sine theta is mv squared over r. And it says if we divide the second equation by the first, F sine theta divided by F cos theta, then what we get, F sine theta over F cos theta gives F tan theta, and mv squared over r over mg all simplifies down to this expression that v is equal to square root of rg tan theta. And since v is equal to r omega, it shows that the time period is basically equal to 2 pi square root of L cos theta over g. So this is the relationship that helps us understand the time period of a conical pendulum of length L. And it's basically very similar to the length of pendulum time period expression of a normal pendulum. Notice the vertical components are exactly the same as in the curved track example that we did a couple of slides ago. And you can just take that expression straight into the exam with you, remember it, but you might also be interested in the sleight of hand, like what was the derivation on the left-hand side when we divided one term by the other? Well, we got to the point where omega was equal to the square root of g tan theta over r. Now, omega is equal to 2 pi over t, that's straightforward. But what we want to do is we want to do 2 pi divided by square root of g tan theta over r, which is the same as 2 pi times 1 over square root of g tan theta over r, which is the same as saying t is 2 pi square root of r over g tan theta. And then what we find out is because tan theta is defined in the formula as r over h, we find that the r on that numerator line cancels out with 1 underneath, and so it simplifies down eventually to t is 2 pi square root h over g, where h is defined as L cos theta. So that is how we did that bit. Maybe have a go a couple of times. It's not essential, but it is very interesting to see how we get to that final result.